Hi everyone, welcome back to Made Everything Official. In the world of heavy industry, reliability starts with the equipment you lift. At Hendrik Veder Group, precision-engineered steel slings ensure every lift is strong, safe, and repeatable, from ports and shipyards to offshore platforms and energy plants. This video highlights the latest addition to their rental fleet, 12 identical steel lifting slings, each measuring 61 millimeters in diameter and 3 meters long. Every sling begins its journey as high-grade, fully certified steel rope. The strands are meticulously laid and compacted to form a dense, uniform core capable of handling enormous tension. In the fabrication hall, trained specialists shape the rope into precise lengths using hydraulic presses. At both ends, steel thimbles are inserted and securely locked by pressure-fused ferrules, creating permanent, high-strength eyes. Each connection is examined under strict quality control standards, including visual checks, magnetic inspections, and proof load testing. This attention to detail ensures that every sling can perform safely, even under dynamic loads or harsh offshore environments. Before entering the rental fleet, every new sling undergoes load testing. Using calibrated testing rigs, engineers apply extreme force to verify elongation, strength, and structural integrity. Results are logged digitally, providing full traceability for every product. These 61mm slings are capable of withstanding loads of hundreds of tons, while maintaining flexibility and corrosion resistance thanks to advanced galvanic protection and lubrication systems. From design to certification, each sling reflects Hendrik Veder Group's commitment to safety, sustainability, and performance. Expanding this fleet means greater availability for customers who demand high-quality lifting gear, delivered fast, tested, and ready for immediate use. Whether supporting renewable energy projects, shipbuilding, or heavy construction, these steel giants stand for trust and engineering excellence. Step inside the production hall where raw steel sheets, copper coils, and high-voltage equipment come together to form one of the backbone machines in modern power grids, the power transformer. Here, precision meets power, and each component is engineered to deliver reliability under years of continuous service. The process begins with the magnetic core. Grain-oriented electrical steel sheets are cut, annealed, and stacked with care to minimize losses and improve efficiency. Next, the coil winding lines take over. Copper, or aluminium, conductors are wound into tight layers, insulated, and prepared for the high-voltage demands ahead. Once the core and coils are ready, they are assembled into the transformer structure. Precision alignment, insulation, and thermal design ensure this machine can handle heavy current flow while remaining stable and safe. With the core coil assembly complete, attention shifts to the tank, cooling system, and protective devices. Radiators, piping, bushings, and oil chambers are fitted to manage heat, pressure, and insulation. Transformer oil is filled under vacuum to remove moisture and gases, ensuring long-term insulation performance. Then the unit undergoes comprehensive testing. Load tests, insulation checks, thermal behavior assessments, and dimensional inspections ensure it meets international standards. Every machine is logged, tracked, and certified before delivery. When you see a power transformer installed at a substation or within an industrial plant, you're looking at the culmination of dozens of precise processes, countless hours of craftsmanship and rigorous quality control. In Augsburg, Germany, engineers at the Center for Lightweight Production Technology are redefining how large aircraft components are built. Their research focuses on highly automated production of dry carbon fiber composite structures, the foundation for stronger, lighter, and more efficient aircraft. The centerpiece of this project is the rear pressure bulkhead, a 5-meter-wide structural element composed of multiple layers of carbon fiber textiles arranged in complex double-curve geometry. Automation begins with the precise placement of the first fiber layers. Special robotic end effectors unroll the carbon fiber sheets directly from the material rolls, draping them onto the curved tool surface with perfect alignment. Each motion is monitored and adjusted to maintain fiber tension and contour accuracy. To fix the plies in place, an epoxy resin, later used for infiltration, is lightly applied, eliminating the need for additional adhesives and saving time in downstream processing. Next, smaller reinforcing patches are prepared. Automated cutting machines trim each patch to exact dimensions. Grippers equipped with over 100 suction modules lift the pieces, detect their orientation with optical sensors, and adapt their shape to match the tool's contour. As the patch is laid, the suction modules adjust individually, pressing the fibers smoothly onto the mold surface while monitoring draping quality in real time. For larger plies, two collaborating robots work together. Their end effectors are reconfigured to the exact tool geometry, gripping the long carbon sheets from each side. An adaptive algorithm calculates collision-free motion paths, sending the commands directly to the robotic cell for synchronized placement. Every step, gripping, draping, pressing, is digitally coordinated with sub-millimeter precision. A fiber angle camera verifies the orientation, while a laser sensor inspects the edges of each layer. The result is perfect stacking and fiber alignment, crucial for the mechanical strength of the composite structure. Once the layers are complete, stringers, the stiffening elements, are automatically positioned by a multi-kinematic gripper. Vacuum suction arms hold each piece securely, then reorient and place it precisely onto the preform. Human operators supervise final positioning of auxiliary material packages, assisted by a digital twin model that coordinates safe robot paths and collision-free motion. This hybrid workflow blends human judgment with robotic precision, ensuring both flexibility and safety. Finally, a semi-permeable membrane is applied for vacuum infusion, and the entire preform is infiltrated with epoxy resin before curing. The result is a flawless carbon fiber bulkhead, lighter, stronger, and produced with unprecedented automation efficiency. This is how the future of aircraft manufacturing takes shape, robotic precision meeting human innovation, driving the next generation of aerospace technology. Welcome to a new era in aviation manufacturing. Here, engineers and researchers are building the MFFD, the Multifunctional Fuselage Demonstrator, a large-scale fuselage section designed to redefine how airplanes are made. With a length of 8 meters and a diameter of 4 meters, this structure sets a benchmark for what the future of aircraft production can achieve. Unlike traditional aluminum fuselages, the MFFD uses thermoplastic carbon fiber reinforced composites, CFRP. These materials enable lighter weight, fewer fasteners, and faster production. In this program, more than 40 separate technologies were integrated, from automated layup to advanced welding and assembly processes. The structural shells are produced in 2 halves, pre-equipped with systems and modules, then joined with automation enabling high-rate, dust-free assembly. In the production hall, robotic tape-laying heads place composite plies automatically, continuously, without the need for an autoclave. Stringers and structural frames are welded to the skin via ultrasonic and resistance welding processes in minutes, a world first at this scale. Hexapod robots align and correct the shells in all 6 degrees of freedom, ensuring sub-millimeter precision in assembling large structural components. The MFFD is more than a demonstrator. It's a blueprint for the aircraft of tomorrow, lighter, faster built, more sustainable. By reducing structural weight, enabling system integration early, and automating large-scale assembly, the aerospace industry is moving toward greener skies. In the world of railway infrastructure, time and precision define success. Today, we introduce a new construction concept from RF System AB, designed to make track laying faster, safer, and more cost-effective than ever before. The system begins with specially designed tools and attachments that work seamlessly with excavators and track-laying machines. Laser measuring modules ensure sleeper spacing is exact, while multiple grip modules allow rails and sleepers to be handled simultaneously. The result? One machine, one pass, multiple operations, reducing the number of lifts, alignments, and rechecks required. With this new concept, the track foundation is laid in a single integrated workflow. First, the rail and sleeper bundle is lifted, aligned, and set on the prepared sub-ballast. Sensors monitor placement in real time, ensuring both longitudinal and lateral alignment. Next, fasteners are applied in-machine, reducing manual labor and enhancing ergonomics. Meanwhile, quality control modules record each placement event, offering traceability and supporting long-term maintenance planning. The result is clear: fewer machines on site, less traffic interruption, and a faster route from raw materials to operational track. In the high-speed world of paper production, the Headbox plays a critical role in delivering uniform sheet formation and consistent product quality. At ANDRITZ, specialists perform a high-performance overhaul of this vital component, restoring machines to peak condition and extending their operational life. Over time, headboxes suffer from corrosion, wear at the slice and apron lips, and damage to heating channels, all of which threaten production stability and sheet quality. The overhaul service covers full disassembly, replacement or repair of worn parts, precision machining of critical surfaces, installation of new heating units, and final adjustment of all components. The result? A new headbox with restored performance, capable of supporting stable sheet profiles, safe operation, and long-term production reliability. When your production line depends on consistency, downtime is not an option. With ANDRITZ's Headbox reconditioning service, mills can reduce risk, maintain high quality, and avoid replacement costs. Welcome to one of the world's most capable plate rolling operations at North Shore Steel. Here, heavy steel plates are formed into large cylindrical shells for pressure vessels, structural tanks, and high-demanding industries. The machine you're watching is the Davi MAV, a 3-roll variable-axis plate roll built for flexibility, precision, and heavy-duty performance. At North Shore Steel, the setup handles plates up to 10 inches thick and forms diameters up to 22 feet, a facility built for the largest plate rolling jobs in North America. With the 3 motorized rolls, the top roll tilts, the lower rolls adjust positions, and the combination allows cone bending and large diameter cylinder forming with excellent roundness and minimal flat ends.